Hey, hi, how are you all, champs? I hope you all are doing well. Okay. So, as you know, that my name is Brahmastra and I am here coming with the second lecture of Electromagnetic Induction for you all. Okay. So, please, I hope we have already gone with the first lecture. Right? If you did not watch the first lecture, please watch the first lecture, understand the basic things we have covered there, the basic important thing that is about what? The magnetic flux. Right. So, here we are come up with the second lecture where we'll first solve the few questions, one or two questions of the magnetic flux, and we will just memorize the few important formula what we have studied gone through it right in the previous lecture. And again now we'll start with something new that is related to lecture. Okay, but before do it, I would request you the same thing. This lecture I will started just to make you guys very comfortable with the things that physics is very easy for you. This is the very important thing why I started this lecture for you all. Why? Because I just want to make you comfortable with the physics. So it's my humble request, beta. Please, if you want to make your physics basics well, please watch this lecture, understand the concept. After that, as you know that I always used to say, please discuss with me. If you are the free user, you don't have any, you did not purchase any course, don't worry. Just go in the comment box and ask with me the doubts. I will resolve it in the next lecture. Okay. Second thing is that if you are the BTS user or the Elite user, then you have already the WhatsApp support group there. You can already ask any doubt with me by tagging there. Okay. And as you already know that because of my busy schedules, I get very less time. Sometimes I will respond in the WhatsApp by delay, like after not instantly, but yeah, I will respond your all the doubts, sure. As I always used to do, I guess, right? Those who are the paid users, they already go know about it, right? So guys, let's start the lecture, right? And hope you are all like awakened, you are not sleeping while watching the lecture. Please, little bit awakened. Okay. जग जाइए आप लोग. Fine. Let's start the lecture without delaying that. Right? So yesterday we gone through with the magnetic flux, and one important formula was with us. That was what? That was like phi, the magnetic flux. Sorry, what I'm writing. Phi magnetic flux is equal to what? B dot A means B is what magnetic field vector and A was area vector, right? So it was coming out B A cos theta, right, guys? Hope you all know it. We have already gone through it yesterday, right? That theta is what angle between magnetic field vector and the area vector. Area vector was what? Nothing but the normal to the plane outward side. Okay, this is the first thing what we have gone through yesterday. So here on the West axiom we have a numerical what it is saying. Find magnetic flux linked with the ring such that it is placed as on its axis a straight wire carrying current passes. But it is saying, understand the word here, that we have a ring, okay, and on the axis of that ring a current carrying wire is passed. Okay, it is shown here. This is nothing but this is what is our current carrying wire I. Got it? Clear? Now what it is saying to us that beta, we have a ring here, a ring like this. This is like nothing but it is like this. Understand this. This is wire. This is wire. Current is going in the upward direction like this. Okay, and ring is placed here beside it. Okay, ring is placed here like this inside it. See, this is the ring. Hope you can assume it, right? This is the ring which is placed like this. Now I'm just asking with the question that understand. We all know that the magnetic field is nothing but it will be curl and perpendicular to this wire and in the curly direction. It means magnetic field will be always like this in this direction. So here for understanding purpose, we can understand that magnetic field will be like this. For any instant, it will be like this only, perpendicular to the wire, right? But area vector will be perpendicularly outward, means upward direction. So area vector will be like this. And magnetic field vector is this. The angle will be what? 90 degree always. You can take at any instant this magnetic, because we all know that magnetic field is like basically curly. But it is always perpendicular to this wire. So if it is curly, from right hand thumb rule, I think you guys can remember, right? If it is curly beta, then always perpendicular to this. I mean, it will be always in this plane one. In this plane, it will be only. Magnetic field will always be in this plane. For example, this is our wire, right? Then magnetic field will always be like this, in this plane only. It will be always in this plane only, right? But our area is already upward. Understand? So angle will always be 90 degree between magnetic field lines and area vector. So that's why the value of magnetic flux here linked with this ring will be 0. Hope you got it. The phi will come 0. Why? Because theta is here 90 degree. Hope you got it. Right? Theta is 90 degree, so cos 90 is 0. That's why phi is equal to BA cos theta means cos 90 is 0. The phi is 0. So this is the question which I wanted to tell you. On the same basis, there are various questions, right? The question can be like this: if we have a understand, this is solenoid. We have a solenoid, right? Hope you got it. And a circular, or we can say like a rectangular coil is placed along the axis of the solenoid and parallel to its axis. Or it is placed parallel to its axis. Understand? The solenoid is placed like this, and its solenoid on this solenoid there, the coil is just like this, parallel to its axis. Parallel to its axis. So if it is placed parallel to axis, then we all know that what the magnetic field is already along this direction only. Along this direction only, understand? Outside this is like this in the solenoid it is like this now only. Along the axis of the coil only. But area vector is now again here outward normal. Because see, we have this coil along parallel to the axis of the how it has been placed. It has been placed like parallel to the axis of solenoid. And so area vector will come outward normal. But we all know that inside the solenoid, the direction magnetic field is nothing but it is along the what? It is along its axis. So that's why angle will again be 90 degree. Because see, plane is this rectangular plane is along axis parallel to the axis, but its area vector will come perpendicular to it, na? Perpendicular to the plane, so it will come out. And this magnetic field is along this plane only. So angle is 90 degree. Angle is 90 degree means again the flux linked with this rectangular coil will be 0. This question can also be asked from you. Hope you got it, guys, right? So now without disturbing, sorry, without taking a lot of time, we'll go with our the next part, that is nothing but what? Lenz's law. But before to it, I would like to tell you two important things. That is, the first thing is what? If we have a coil, understand it very clearly. If we have a coil beta and magnetic flux linked with that particular coil is constant, means the magnetic flux is what? Constant. If it is constant beta, then no induced current will be there. Induced current will be 0. Right? We got it? The induced current will be 0. But if, understand, if with this loop the magnetic flux linked with it is changing, it means what? There will be induced current, that will have to remember, and direction of induced current will be given by Lenz's law as mentioned here, and magnitude of the induced current will be given by Faraday's law. So today we will go with first Lenz's law, means we will try to find out the direction of the induced current in different cases. Okay, and then tomorrow lecture we will go with Faraday's law. Hope this much is clear for you. Second important thing, but Lenz's law, I think you already know it, but I would like to explain you here that as per Lenz's law, what he said, whenever the magnetic flux linked with a coil is going to change, then then the current will be induced in that coil. That current is called induced current, and direction of that induced current is such that it will oppose the change in the magnetic flux. It will oppose the change in the magnetic flux. Or here it is also written, if magnetic flux linked with the coil or loop changes, then direction of the induced current in that loop will be such that it will oppose the cause of induced current. Cause of induced current is nothing but the magnetic flux changes. Because see, if magnetic flux with linked to a coil changes only, then induced current will be induced. It means the direction of induced current will always be such that it will always try to oppose the change in the magnetic flux. It will always try to oppose the cause of its production. So cause of production is what? Magnetic flux. It means the direction of induced current will always be such that it will always try to oppose the change in magnetic flux. It means if magnetic flux linked with a particular coil will increase, then induced current will be such that it will try to decrease it. If magnetic flux linked with the particular coil is decreasing, it means the induced current will be such that if we try to increase the magnetic flux with the coil. Hope you got it. But just it will oppose. The direction will be such that of induced current that it will oppose the cause of its production. Cause the production is what? The change in magnetic flux. If magnetic flux is increasing, so it will be the current induced will be such that it will try to decrease the magnetic flux through that particular what coil or loop. But if magnetic flux in with the loop is decreasing, then induced current will be such that it will try to increase the what? It will try to increase the magnetic flux. Why? Means it will always oppose. So the direction of induced current will be such that it will oppose the what it will do? It will oppose the cause of its production, which is nothing but changing magnetic flux. It will always be in such a way that it will be able to oppose the change in magnetic flux through that particular coil. That you will have to remember. Okay, I think it is clear. That is the 2 points which is being mentioned, which I wanted to tell you as per Lenz law. Now the two important things which you should remember here that see there are two such criteria like if magnetic field is perpendicularly inside the plane of paper, then it is mentioned like this in our scientist or in our scientific way or in our study way, mathematical term cross. If direction of magnetic field is perpendicularly inside the plane of the paper, then what we say it is cross. Okay, and if direction of the magnetic field is perpendicularly outside the plane of the paper or toward the reader, then how we mention it? We mention it by dot. For a region, if magnetic field is what? Perpendicularly outside the plane of the paper, then what we will say? We will mention it by direct dot. If it is perpendicularly inside, we will mention it by cross. For example, for this region, it is perpendicularly inside, so we mention by cross. Here it is like this. Why? Because it is mentioned by dot, right? Means it is perpendicularly outward. That is it written in first and second point. Third point, it is written that magnetic field originates from north. As you already know that magnetic field always originates from north pole and goes toward the south pole, right? So for understanding purpose also we can understand that here magnetic field is perpendicularly inside, means inside means it is going away from me. It means the part from where it is going, the part, if we treat this as an imaginary magnet, this region of magnetic field, then we can say that the part which will be toward us, toward the reader, right? It will be north and away part will be what? South. In the case when it is going inside. In the case when it is coming outside, normal perpendicularly outside toward the reader, in that case what we can say that the front part which is looking, that will be like a, for imaginary magnet I'm taking, south, and back end part will be north. Okay, that I wanted to tell you, explaining. That is the second thing which I wanted to tell you. Apart from it, beta, the most important thing which I wanted to tell you here, guys, that coil is placed inside a magnetic field in different cases. Exactly. See, beta, here it is very, very important which you will have to understand, right? But you will have to understand this, you will have to understand. See, there are four cases which you'll have to remember as it is, because see, it is not like very important as per Neet, because till now it has not been asked in Neet. So you will not have to worry for it. Just I'm telling you, you'll have to just remember it as it is. Okay, it is not very important as per Neet. See, but it is if magnetic field, understand, if magnetic field is perpendicularly inside, the magnetic field P is perpendicularly inside means cross, and it is increasing. It is perpendicularly inside in a region, understand this. It is a region in which magnetic field is there, and we have mentioned by cross here, right? It is increasing this value. It is uniform everywhere, but it is increasing. It is increasing, and if we placed any coil inside it, then what will be the direction of induced current on this coil? That you will have to remember. How you will remember it, but it is very important to remember, and please remember as it is, because see, if I'm going to tell you the concept, then it will be very complicated for you. That's why, because it is not very important also, but I wanted to tell you 4 points which will help you a lot. Okay, first case is what? If magnetic field is cross, means perpendicularly inside the plane of the paper for a region, and there a coil is being placed such that now magnetic field is increasing. So if magnetic field we are trying to increase the value, then what will happen? The magnetic field link, sorry, magnetic flux link with this coil which is inside here, circular coil, that will also going to increase because it is already placed inside it only. So the magnetic flux is already going to induce. I think you can already see, already understand it. So if magnetic flux is inducing, sorry, magnetic flux is changing, the EMF will be induced. Sorry, the EMF will be induced and current will also be induced. And diaphragm induced current will be like that. What? That you'll have to remember that in the first case, the diaphragm induced current will be what? It will be anti-clockwise. That you will have to remember as it is, without anything. If magnetic field is perpendicularly inside and it is increasing, its value is increasing, and in that region, if you will put a coil, then the induced current on that coil will be anti-clockwise. That is the first point. Second point is the same thing. What if this value is now decreasing? The same thing. But here we have a region in which cross magnetic field is there everywhere same, but now this value is going to be decreasing. We are decreasing the value with time, this value everywhere, and now we placed here a coil. So since we are decreasing the magnetic field, so through this circular coil also the value of magnetic field will change, decrease. It means with time, it means sure there will be induced EMF or induced current. The diaphragm induced current will be in such case what? You will have to remember it as it is. What it will be? It will be clockwise. That you will have to beta remember. Will be clockwise. This is the second case. Third case is now for perpendicularly outward. These two cases was for perpendicularly inside, and third case will be what? Perpendicularly outward. Right? See, this is what. Now here dot I am showing. Dot means what? The magnetic field is perpendicularly outward. Everywhere it is uniform. Right? Now what happened? We put it here a circular coil and we increased its magnetic field value B of this whole region, and coil is already placed there, so magnetic field link with this coil will already increase. I mean magnetic flux will link with this coil will increase. If this coil magnetic flux will increase, this then your EMF is going to induce in this circular coil, right? If EMF will be induced, then diaphragm induced EMF or diaphragm induced current will be such that how it should be clockwise. Remember it will be clockwise. That you will have to remember it, right? It will be what? Clockwise. Hope you got it. Second case, what? Same thing. You'll have to remember as it is. Why I'm saying? Because see, something, if I'm going to explain you now, then it will consume your more time, which is not even very important. I'm just requesting you to remember it as it is, okay? But is this here that same thing here? Magnetic field is there, right? Coil is placed there. It is perpendicularly outside magnetic field now, and now its value is decreasing. Its value is decreasing, this magnetic field. So of course, if it is placed inside it, so of course the magnetic flux linked with this coil, circular coil, which is inside it, will also going to decrease. So if magnetic flux linked with this coil is going to decrease, then EMF and hence induced current will also be induced, and diaphragm the induced current, that is very important for you that to remember, that is anti-clockwise. Okay, so what you will have to remember, these are the four cases which you will have to remember. That first case I told you what? Wait, first case what I told you is that remember, write it as it is. What? B is cross and increasing, so current will be what? Induced current will be what? Anti-clockwise. Second case what I told you, B is cross but it is decreasing, so current will be what? Clockwise. Third case what I told you beta, what I told you that B is dot but it is increasing, so now current will be what? Clockwise. And fourth case what I told you beta, that again B is what? Dot but it is decreasing, so current will be what? Anti-clockwise. You can remember it like this, that whenever, understand it, whenever the magnetic field will be inside, then in that case if it is increasing, only then the current will be anti-clockwise. And reverse, you can remember that reverse will be always clockwise, right? And whenever current is, understand it, whenever the magnetic field is outside but it is decreasing, then current will be anti-clockwise. For other two remaining cases will be already clockwise. That you will have to better remember it as it is. Okay, I'm just explaining it. Sorry, just saying the same thing again so that you guys will remember it. What I said. These are the four cases. The first case is what? If magnetic field is perpendicularly inside and its value is increasing, then what will happen? Then the induced current will be anti-clockwise. Second case, I am telling you. Sorry, this is the second thing which you'll have to remember. That is what? If magnetic field is perpendicularly outside, but its value is decreasing, then current will be anti-clockwise. These are the two cases for anti-clockwise. For clockwise, already automatically you guys can be taken it reverse. Okay, these things will have to remember it better, which are very important. Now see here, this is very important thing I wanted to tell you here, but I guess it is already something wrong has happened here, so we'll have to first delete these things, right? But I'm deleting it better for you all, then I will explain you again. Okay, sorry, something wrong has happened here. I guess someone has used this file, or I only used, I don't know it. Just wait a moment. I guess you remember all those points now. For anti-clockwise case, you just have to remember what? First case, magnetic field is inside, perpendicular inside. It should increase, only then current and the induced current will be anti-clockwise. In the second case, the second scenario, right? What was? If the magnetic field will be perpendicularly outside and then it should decrease with time, only then the current induced will be what? What beta anti-clockwise. Okay, that much only you will have to remember. Okay, everything is fine. So now this is the another case. What is saying that the case of uniform magnetic field and coil is crossing the region of uniform magnetic field. Okay, here it is saying that beta, understand it. It is only based on the above 4 point. Okay, that you'll have to remember what I told you, right? Now understand. Here we have a region. Understand? We have a better region in which uniform magnetic field is there, which is dot. Dot means what? Now I am saying dot. It means it's perpendicularly outside. But just you will have to keep it in mind. Perpendicularly outside, what was? What was the case perpendicularly outside? The magnetic field will decrease with time for a coil. Understand? For a coil, magnetic field is decreasing with time. It means what will happen? Current will be anti-clockwise. If it is increasing with time for that particular coil, okay, then current will be clockwise. Fine. So sorry. From where it came, I also don't know. It is not working. Fine, beta. I have to redraw it again. I guess this boundary. Okay. So see, we have a coil now, circular coil, which is moving inside it. It is moving inside it. Okay. So as soon as it is outside, of course, I think you can easily understand that there is no magnetic field. So there will not be chances that any change in magnetic field or link with this coil. So there will not be any induced EMF or induced current, which will be zero, right? But as soon as it will come over its boundary, it will touch the boundary and will start entering here. Now what is happening here? Understand it. The magnetic field link with this coil is increasing. A scenario you remember, I guess. What is the scenario? For in a perpendicularly outside case, that whenever my magnetic field link with a coil will decrease, then current will be anti-clockwise. Else means the magnetic field link with a particular coil will increase, then current will be clockwise. So here what is happening? Here the magnetic field link with this coil, circular coil is increasing. So it is which case beta? It is here, understand it from here where it gone. I don't know where it gone. This is this case. This case it is. This case. Magnetic field with the coil was increasing. It doesn't matter how it is increasing. Understand one thing. The magnetic field, if I am saying it is increasing, it doesn't matter that how it is increasing. That it is moving inside or it is there only and magnetic field value increase. Anyhow, if it is increasing with this coil, circular coil, right? Then scenario will be what? The current will be clockwise. That you will have to remember, right? The same thing is here, better. Here what happened? The magnetic field link with this coil is now increasing because as soon as it will come inside, the maximum part will cover inside. So magnetic field link with this coil will increase. Magnetic flux with this coil will also be going to increase. Magnetic field means increase. The magnetic flux is already going to increase with this coil, right? So what will happen? What will happen? The current will be here. The induced current will be here clockwise. Hope you got this point, right? And similarly for this, if it will come inside region, then already magnetic field is everywhere same. Magnetic field is same, so there will not be any induced current. So induced current will be here what? Zero again. When again it will come here by traveling this outside part, since it is moving already right everywhere. Again if it will come here moving, when it will start going outward, then again what will happen? The magnetic field link with this coil, or hence magnetic flux link with this coil will start decreasing. If it will start decreasing, then you remember that what is the case here, as we studied right now only. That case was what? This is the case. This case. But the magnetic field link with this coil will be changed, will be decreased, then the current induced will be here what? Beta anti-clock. Okay, hope you got it. So now induced current will be what? Oh, wait. Arey, yaar, it is going away. I don't know why. It will be what? Anti-clockwise. This you will have to remember. Okay. So this is another question. What is saying? When the conducting wire XY move toward right, a current flow in anti-clockwise direction. Find the direction of magnetic field point. It's the same thing on the basis of same 4 points. See how it is saying. We have here this a circuit. Okay, understand it. And this is movable device, movable wire. Its name is XY. This is movable wire. Its name is XY. It is moving here. It is moving inside here. Understand it. And it's saying current flows in anti-clock. If it is moving inside here, then and here it is saying it's a magnetic field there. Because if there will be magnetic field better na, only then see this area. If it will move inside this region, what is happening? This is movable. This wire XY it's movable over it. It is moving over it. So if it will go inside it for after part time, after few time better, then what will happen? Its area will decrease. Area will decrease means this area will decrease means magnetic field link with this coil will decrease. This region, this complete loop region will decrease. If magnetic field link with this region will decrease, then what will happen? The current will be anti-clockwise, which is given here that the current is anti-clockwise. It means what? It means what? The scenario is what? The magnetic field is perpendicularly outward. Magnetic field is what? Perpendicularly outward. Why? How we got this? We got this by this, that here it is given the current is anti-clockwise. Induced current is anti-clockwise. So induced current is anti-clockwise in only, and area is decreasing. Area is decreasing, magnetic field is decreasing. So beta magnetic field decrease and induced current is what? Anti-clockwise. In which case it was? You remember? It was in perpendicularly outside case, fourth number case. You can remember. See, this is the fourth number case where we discussed about this, right? That's why we got that. This is the, now I guess no issue with this. With the next question, what is it there? An irregular shape loop is now starting to convert into sub. It's the same question again. See, again the same thing is here. Here this question is that like this. See, we have a uniform magnetic field perpendicularly outside. We are giving dot mid perpendicularly outside. Understand it? We are perpendicularly outside, right? Here it is given that initially we have a coil. This is irregular shape coil. This is irregular shape coil we have. This I think you can remember. See it right now. Now it is increasing. It's a size from everywhere, and it is converting into a circle. Hope you can see it clearly that if it will convert into circle beta, then its area will increase. Total area of this region will increase, because right now it is less. When it will convert into like circle, this its area will increase. It's common sense, because it is increasing now. It is expanding, so area will also expand for common understanding. If area will expand, then what we can say? The magnetic flux link with this region. Because more regions, so more magnetic field lines. More magnetic field lines means what? More magnetic flux. So magnetic flux is going to increase. Understand? Magnetic flux going to increase. And if magnetic flux beta going to increase, right? Then I think you can remember for perpendicularly outside case. It is given that magnetic field is perpendicularly outside case and magnetic flux is increasing. It means current will be what? Clockwise. Clockwise. You can remember the case number 3 is here, beta. Case number 3. See, that's why I'm like, I don't want to make it the things are very complicated. That's why I'm going to with you a very simple way. Case number 3, this is. But case number 3 was the magnetic field perpendicularly outward and coil with coil. This coil magnetic field is increasing. If magnetic field with the coil is increasing, then current will be current will be clockwise in that particular coil. Hope you got it this much, right? Now move with another question, beta. Variation of flux with time for a loop moving inside the aluminum form. I think you can do it very easily, beta, right? See how you can do it. Understand it. It is saying that what it is saying, we have a region. We have a uniform magnetic field region. It is perpendicularly outside, you can see, or perpendicularly inside, whatever you feel, right? Now here we have a small coil. It is moving inside. We'll have to draw a graph from the time it just touches. It just touches this region. So when it will just touch this region beta, then you can easily see that there will not be any magnetic field attached with this. There will not be any magnetic field attached with this. Since it is moving with constant velocity, so of course it will enter here. As much as beta it will enter, its magnetic field linked with this region will increase, because now this region is coming inside magnetic field. So more magnetic field means more magnetic flux. So we can say that when it will be entering in entering phase, till the time its whole body has been entered, for that particular instant, the graph we can draw like this. We can draw that it is increasing. It is increasing. What? This is time t. This is what? Magnetic flux phi. Why it is increasing? Because magnetic field lines will increase, of course, with this region. Because as soon as the more this region will come inside, more and more magnetic field lines will pass with this rich coil, this coil, this coil. More magnetic field will pass. This meant was what? More magnetic flux will be there, right? So as soon as it will enter, and till the time it is completely entered inside, the magnetic field lines will increase with this coil, so magnetic flux will increase. So this is the instant example we assume when magnetic completely it got entered. Now when it will be completely entered and will start coming here from this point to move till this point, it will come this point till this point. There will not be any change in magnetic field. Why? Because everywhere magnetic field is same and it is moving here. It is moving here only. So everywhere it will be same, since its area is also same. Area is also not changing of this coil because it is same, and magnetic field is also everywhere same. So magnetic flux linked with this coil will remain same. So till the time it will come at this position, the magnetic flux will be like constant. Now again when it will start coming outward, as soon as it will come outward, it's a little part coming outward beta initial case, right? And little decrease in magnetic field. Why? Because area is decreasing. Which is in contact with magnetic field lines, so magnetic flux will again decrease. So as soon as it will start coming out, and when it will completely come out, just touch the boundary, its again the value will be like this. Hope you got it. No doubt with this. This simple concept, I think you can easily understand this concept. Okay, no doubt with this. So this is graph versus what? Magnetic flux versus time graph. Hope you got this much. No issue with this, right? So we'll move with next questions. That is magnet and coil, which is very important beta, and it has been asked in Neet in 2024 also, I guess, right? This question, understand it, it is very important, right? Here we will try to understand it more detail. See, what we have a first case scenario. Scenario is what? We have a magnet, we have a bar magnet, understand? Its north pole is this is its south pole, okay? And this is another thing, that is what? Coil. That is what beta? Coil, or we can say a loop, whatever you feel comfortable, you can see it. Okay, now we are not at for bar magnet, as right now it is at rest. Understand, this bar magnet is at rest, means its velocity, v velocity is equal to 0. It is not moving right now. So we can understand it easily that whatever magnetic field lines it will be increasing, whatever will be magnetic field lines coming from this north pole will pass like this. You can understand this pass like this, right now, because in the format this type of process. So of course some magnetic field lines will also cross with this region also, this region, this coil region. But now since whatever the magnetic field lines it will be crossing, it will be constant. There will not be any change in magnetic field lines, since there will not be any change in magnetic flux also, because area is also not changing. Area is also this constant for this loop. and magnetic field lines also constant. But understand the situation when it start moving. What is start moving? This coil or this magnet, anything. First, we'll understand the thing when this magnet start moving. What will happen? This magnet start moving. This magnet start moving. This is north. This is south. Okay, and here we have what? Coil. Now this magnet is start moving, coming toward what? Understand it one thing. When it will start coming toward it, what will happen? The number of magnetic field lines passing through with this region, this particular region of coil will increase. Why? Because now it is coming more closer. So more number of magnetic field lines will start passing with this. It means magnetic field link with this coil is going to increase. This coil. So when beta magnetic field lines going to increase with this coil, number of magnetic field lines going to be more. So magnetic flux is going to increase with this coil. And if magnetic flux is going to increase with this coil, now what will happen? What will happen, beta? Current will be induced in this, and direction of induced current now we'll have to find. We'll have to find out the direction of induced current. We all know that direction of induced current will always be subject, will oppose its cause of production. So here it is cause of production is what? Increasing magnetic flux. So it will try to decrease the magnetic flux. So for decreasing it, what it will try to repel it. Why? What will try to repel it? This coil. So this coil will be converted into a imaginary magnet. Understand? This coil will be treated, can be treated as an imaginary magnet. And what are the reason for inducing the EMF? So inducing the current here, increasing the number of magnetic field lines. How it increasing? Because it is coming more closer to it. So it will try to repel now. It will have to oppose it, na? It will repel. So for repelling, since here it is north, though, so here will also have to be north. Only then it can repel it. Only then it can repel it better. So here it is north. It means here it will be south. You got it? And understand one thing. Always remember it is here as it is here written better. North means anti-clockwise. So if any person is going to stay here, this side, any observer is here, right? This person is here. Anyone, its name might be Pappu. Okay, Pappu is here watching from this side. Then what he will show that it is north. North means anti-clockwise. The current will be what? Anti-clockwise. If someone is watching from this side, understand Gappu. Pappu brother is Gappu. Okay, and he is watching from this side. This side. So what it will show for him? It is north. So north means clockwise. So for him, the current will be clockwise. Means he will watch from another side, and this guy is going to watch from this side. So for him, the current will be what? Hope you got this point. This is the first case what I wanted to explain you. Okay. Hope it is clear for you also. Now second case I wanted to explain. What the second case is? This magnet is now like this. This is north, this is south, and this is again the here our lovely. What lovely we have? Here we have a circular wire. Okay. Now the scenario is like this, beta. Now this magnet is trying to going away with velocity v. So again, the magnetic field lines will decrease with this coil. If magnetic field lines will decrease, then of course the current will be induced because magnetic flux will decrease. Because magnetic flux is just because of number of total magnetic field lines passing through this region. It will decrease because it is going away. So it will magnetic field lines will decrease. It will decrease. It means what? It will the induced current will try to increase it. Increasing means what? It will try to attract it. Why attracting? Because it is going away now. So because of it, only number of magnetic field lines are decreasing. So it will attract it. How it can attract it? If this can be treated as an imaginary magnet, this coil, then for attraction here should be south. Here should be beta south because it is north already. So here it should be south. Only then it can attract. And here should be north. Someone, for example, now again the Pappu is here. This guy Pappu is watching from here. Okay, what he will show? It is showing south. South means what? Yeah, I've written it already. South means clockwise. So for that guy, what it will show? South clockwise. But person who is standing here, the Pappu's brother, Gappu. What Gappu is doing here? He's enjoying here. He said, no, no, for me it is north. So for me it will be anti-clockwise. Exactly, it's the truth. So these are the two different cases which I wanted to tell you, beta. Apart from it, now we will understand few important things also. See what I wanted to tell you. There are various cases which you should understand better. See, now there can be another case. Understand. For example, we have this magnet, right? We have this magnet. This is north and this is beta south. And here we have a coil and here we have another coil. Two coils now we have, right? Please ignore my writings. Okay, guys. This is another coil. Now what I'm saying, this is now this is south and now this is moving like here. Understand it very clearly. But now this is moving here, this side. If it is beta moving this side, then what will happen? The number of magnetic field lines attached with this will decrease. With this will decrease and with this will increase. So if with this coil it is decreasing because it is going away from it, right? So it will try to attract. So for attraction, what will happen here again? Imaginary magnet. Here it will have to create north. Why? Because north, south is there, so north will be this. Now south or north will attract. Why will have to attract? Because number of magnetic field lines is decreasing. How decreasing? But it is going away from it. So north is here means if someone is standing here, right, and he will say this north. North means what I told you right now, anti-clockwise. North means what? Anti-clockwise. So current in this coil will be anti-clockwise for a person is standing here. And if someone is standing here, then beta, then what will happen? Here it is north. It means here is south. For him it will be clockwise. Okay. Now we'll go for this coil. Since it is going close to this coil, so it is moving this side, this magnet is moving this side, this side. So number of magnetic field lines is going to increase for this coil. If it is increasing, what does it mean? What does it mean? Number of magnetic field lines is increasing means it will try to decrease because that is the only region of induced current. It will oppose whatever it will happen. It is very, very, like Kuttagai. It will always oppose whatever it will happen, right? So, what? Now it will have to be decreased. For decrease, it will have to repel. For repulsion, since here it is north, so imaginary magnet we can treat here for this coil that here it should be north for this magnet also. It should be north. Only then north and north will repel. So for where that also we can say for this person what we can say, this is Pappu. For this Pappu again north. North means what? Anti-clockwise. Someone is here standing here, then what he will say? Here north, here it was south. You will say clockwise. That you will have to remember better, right? Another it's a HW for you, but I'm going to give you another HW homework for you. That understand this case. This case is here. Here now it is south. Here it is now north. Okay, here you have changed, and now we have another coil here and another coil here. Understand better? It is very clearly. We have this coil here, this coil here, better. Okay. And what I'm trying to say here that for you, it is moving now this side, again this side moving. So what will be the magnetic direction of induced current for a person here at this position, that is position A. Okay, for a person who is here at this position, understand this position, let's going standing here, this is B guy, for a position who is here, is C. Okay, hope you got it. This is the question which you'll have to solve, and we'll have to share you the answer in the comment box. Or if you are the BTS Elite user, then you will have to give the answer where in the BTS Elite support group. This is the thing which I wanted to tell you. This one. Apart from it, we have another question also. If you will see, right, that question is also very, very good. Better see how that is very good. Understand. Now its scenario is different. Till now, what we were doing that, but bar magnet was moving horizontal direction only. But now we have different scenario. What scenario is this? Understand. This question might be asked this year. Why? Because last year the question has been asked from this, the first last scenario what I told you, right? But it is this. Understand it, guys. We have a coil. Closed coil. Okay. And now what is happening? This is our magnet, bar magnet. This is our north pole. This is our south pole. It is coming toward with acceleration. Something acceleration A. Understand? It is coming outward. Now it is acceleration A. Understand it, very, very important. Okay. Now it is asking that what will be acceleration? What will be the exact acceleration of this magnet when it will come? And when it will come this side, when it will come inside this, and when it will come downward case. Because it is asking when it will come where? Then it will be at this position, when it will be at lower position only. Those two cases it will ask you, for upward position, for lower position only. Okay, understand it. When this coil is closed, means current will flow across this. Current will flow, then induce current will also be, means induced will be, induction will be there, right? Why induction? But this is going downward again, coming downward. If it coming downward, then the number of magnetic field lines with this value is going to be changed. It is closed also, so the current will also be induced. Current will be induced, then it will also try to, but it will try to, number of magnetic field lines will be increasing, so it will try to repel it. It will try to repel it. Repel. It will try to repel it. Beta, it will try to repel it means what? Then of course it is coming with G, then of course its net acceleration will be what? A net. A net की अगर मैं बात करूँ, right? It will be what? Force less than G. Why? Because it is repulsion force will be experienced by it now. Hope you got it. Why repulsion? Because it is coming downward. When it is coming downward, beta, then number of magnetic field line linked with this coil is going to increase. Hence, the magnetic flux will increase. If it will increase, the induced current will always try to oppose it. It will try to decrease it. How it can be decreased, beta? By repulsing. Why repulsing? Because it is coming down. This is the only cause. So it will oppose its cause. Means it will try to repel it. The induced current. So it will try to repel. Repel means upward direction of repulsion. Repulsion means if it is coming with G acceleration initially, then of course its net acceleration will be what? Less than G. Hope you got it. Similarly, if it will come at this position, understand this. It will come at this position now. Only two cases I am taking. No need to solve at center. Okay, good. But it is at this position. Understand. If it at this position beta, then also the A will be less than G. How? See here. If it beta at this position, then again here it is south. Here it is north, as it is upward or south or downward or north, right? Now it is going away, and it is going away. But if it is going away from it right now, so magnetic field lines attached with this coil is going to be decreased now, as it is going away. So beta, if it is going away and magnetic field line is going to decrease, so magnetic flux is going to be decreased. If magnetic flux linked with this coil is going to be decreased, then current will be induced in such a way that it will try to oppose it. So it will try to oppose the decrease of magnetic field now. How it can oppose? By attraction. Now it will try to attract it. So again, attraction will be upward, and we already know that G always downward. Net will be what? A net will be always again G minus A. G minus repulsion rate we can say. Again it will be was less than G. So A net will always be here less than G. That you will have to remember. But here it can be another question that if this coil is not closed, understand this. This coil is not closed coil. It's like this. Then the acceleration will be always equal to G. Why? Because if it is not closed, then there will not be any induced current. I think you already know, because circuit will be complete only then current will be induced. So current will not be induced and there will not be any scene. No scene means no repulsion, attraction, nothing, because everything was just causing because of induced current only, right? And induced current will not be there, so again A will be equal to G. A net will be equal to what here? G. In this case, if it is falling downward, right? This magnet. Hope you got it. This is the thing which I wanted to tell you extra. Apart from it, I have few questions also, right? Those questions I want to give you as a homework. The first question which I wanted to give you as a homework, I'll have to see from my talk. That question for you guys is, I think I have discussed this already with you. Yeah, I have discussed each and everything, I guess. Nothing is remaining for you guys, I guess, right? Yeah, I have discussed everything better. So I think we don't need to worry for it. I think I have discussed everything, but yeah, everything I have discussed, so you'll not have to worry for it, right? Fine. So now tomorrow we'll discuss with what Faraday's law of automatic induction. Okay. So whatever things I today explained you, that you will have to remember. First thing what I told you about those 4 points, that you will have to remember, right? What are the 4 points? If magnetic field is perpendicularly inside and it is increasing for a what? Any coil which is there, for any coil which is inside that, then what will happen? The current will be what? Anti-clockwise. And reverse will be clockwise. Again, similarly, if magnetic field is outward normal perpendicular outward means toward the reader, in that case, if there will be any coil inside it, right? Any coil inside it, what will happen beta? In that case, any coil will be inside it, and for which if it also the magnetic field decreasing only, then current will be anti-clockwise. But others was what others? Other will be clockwise only. Okay, this is the four cases which we discussed initially. After that, what we discussed about different numericals which we need to solve. Apart from it, there is nothing very important which you should remember. But yeah, the magnet case you will have to keep it very in mind. You have to keep it in your mind because that can be asked next year also. Okay, the magnet case, the magnet 4 5 cases which I told you about magnet. There can be another question also. See, instead of magnet, it can be given that yeah, what that coil now can move. That coil can move. Magnet will be rest while is moving. Again, the same scenario will be there. I think you can understand it also, right? You can solve this question in your homework. See, if instead of this magnet is now at rest. Okay, and now this coil which was here, now it is moving here inside, close to this. What will be the scenario? Okay, for current induction, direction of induced current. So today we discuss about direction of induced current. So tomorrow we'll go with Faraday's law of electromagnetic induction. So guys, it's already 1:24 a.m. So bye bye. See you tomorrow. Okay. Hope you enjoyed the lecture. If you have any doubt, please again I would request you please comment it here. Okay. Bye bye, buddy.